So we've come a long way. This is like the longest set of slides in this class. It's 3 lectures long. So we learned how to make functions that return stuff, that don't return stuff, that just do things for us. We learned how to test the functions that we've made by making new testing functions. We've learned about how functions get called and how they execute and how they know who to return back to. That's the stack. And then we've learned about references, a nice way to pass along somebody else's variable to another function. Okay? And then also how to build up a bunch of libraries to make programs with multiple files. And the last thing we did was an extended example, making that counter library. Okay? So we've come a long way, just a little bit further to go. All right? So the next thing that I want to tell you about is const. When you put const in a parameter, you already know what const means as a variable. It just means you make a constant, it can never be changed again. You can put the word const at the front of a parameter name before its type, and that lets you not be allowed to change it within the function. Okay? So this will kind of answer this question, this silly little question. So let's say we like the idea of passing things by reference, right? We save a lot of memory by passing things to functions by reference. Remember this example? Instead of passing a giant vector and it getting copied to the function I want to work on it, we could just pass it along as a reference vector in ampersand. Then it is not copied. That's beautiful. But the second you use a reference, right, you are now allowed to touch somebody else's stuff. And maybe you don't want that. Maybe you just want the memory savings, all right, using references in function parameters. But you don't want to accidentally modify that variable that you pass. You just want the memory savings, okay? So like remember our inc function, void inc. It took an int by reference, I, and that allowed us to change somebody else's int variable. Or we passed along x in main or something. But this is going to change whoever's variable that was a real int that got passed to us, right? And then if we pass along a vector, we'll do it like this, vector int ampersand v. What if we just want the memory savings, like from this, but we don't want to accidentally modify that thing? What you can do is put a const out in front. You say const vector int reference v. That's the trick. That will allow you to get the memory savings of a reference, but you're now not allowed to touch the value there. That's pretty cool. So yeah, let's talk about this. I have an example. You're allowed to assign any value to a constant variable, and this is going to be why this makes sense. Okay? In particular, you can assign a non-constant variable into a constant variable. Let me show you that in main. Const all over again. So int x equals 42. I can totally make a const int y and make it hold the same value as x, right? That's not a problem. I can say x plus plus. The one thing I can't do now is say y plus plus. They got that old 42 value and it's not allowed to ever be changed now. Right? That's going to give me a compiler error. So yeah, increment of read-only variable y, can't do that. But I was allowed to set y equal to somebody else that was not a constant. That's essentially what's going on if you have a constant parameter to a function, because somebody's initializing it in this kind of way. All right? So this means you can pass along regular variables to functions that accept const parameters. All that means is that those functions can't change the value that was passed to them. That's really nice when you have references too, because then you get the memory savings plus the safety of not being able to modify something. Okay, so when in doubt, I would always prefer it if you just reached for a const reference first, and if you notice you really needed to not have one, then take it away. But use them as much as possible. All right, so let's make a sum of vector function using a const reference. So let me make a vector. I better include the vector library. So I'll make a vector of ints called just v, I guess. 1, 2, 3, 4, 5. Let's make a function that takes this vector and sums all the values inside of that vector. Why not? So C out, we'll call it sum vector. It'll take v. So here are my options. Option 1, int sum returns an int, right? That's the sum of all the things in the vector. Option 1 is take it by value, right? There's no ampersand here. It's getting copied. If this was a giant vector, that would be very unfortunate, right? So int sum equals 0 for every element in v, added into sum, and the out. The result is that sum variable. Oh, sorry, sum is elem, not v. Silly me. So this will work, but it's just copying that entire vector. That's no fun, right? It will correctly do it, but it's making 2 copies of this. One for main, one for the function call. One for the function. And apparently the answer is 15. Does that make sense? 9, 10, yeah, 15. Cool. So this is making a copy of the vector. Somebody's initializing it to be like vector int v equals mains v. It's becoming a copy. Do we remember that? Does that still make sense? If I want memory savings, I can make this a reference. That means it'll be set up like this. Somebody's going to say, in that interfunction dreamland, vector int reference v equals mains v. And so now I'm allowed to access mains v. I'm not copying anything. Just the same thing. So it runs slightly faster, though it's so quick you didn't really see a difference. But what I'm allowed to do now is touch something inside of that vector. I'm allowed to say something like this, right? V at 0 equals 42. That's totally fine and totally allowable in a function that's just supposed to sum that vector. And we are touching somebody else's memory right now. This is mains memory, mains vector, because it's a reference. So if I were to print out the vector after this call, it's going to hold 42, 2, 3, 4, 5. Does that still make sense to us? References allow that to happen. We don't want that. We don't want this to be possible. And so what we'll do is we'll make it a const reference. You say const vector int reference v, and it will get initialized just fine. Const reference vector int v equals mains v in the interfunction dreamland when it's getting initialized. But then we're not allowed to touch v. We're allowed to use its values, but we're not allowed to change its values. It is a constant at this point. It's getting up-converted into a constant. And so now I get the compile time error. This won't even compile because this is wrong. It's a constant. We get the space savings of references, but we cannot accidentally modify anything. Okay? So I have to take that away. I'm forced to take that line away if I want this to compile and run. So this is the best version of this program. Take v as a constant reference. No copying, no modification possible. Okay? Any questions about that? It really just comes back to the idea of you can initialize a constant to be somebody else's variable. That's totally fine. Is that a question over there? Yeah. This is a fancy range-based for loop. This colon means in, so you read it as for every int element in V, it's going to range through V and have elem have a chance at being every single element in order. So elem's going to be the 1, then the 2, then the 3 every time we hit the body, and then it will stop the loop once it's visited every element. Put them all into sum. Any other questions? So yeah, that's useful. Constant references, use them as much as humanly possible. Will save your life one day, probably. Okay? We good to move on? Okay, next thing I want to talk about, algorithm complexity. If you would like to check out right now, you do not have to listen. I'm not going to test you on this, but it's a really good time for you to hear this, I would say. This is one of the main concepts of CSCI 41, so not this class. So you're eventually going to need to know it if you take that class. But this is going to help you as you're programming for the rest of the class if I teach it to you now. Just give you a sneak peek, right? So the complexity of algorithms. Let's talk about that. How complex is what I am writing, all right? So it comes back to the question of how fast is my program? Because faster programs are less complex in terms of time, at least, right? So you can always just time your program. You can count how fast it runs with ctime. There's like a clock function. You can be like, all right, my program took exactly 5 minutes to run. That's better than the old version of the program that took 10 minutes to run, something like that. That's one way of measuring it. But there's an issue with doing that, with like taking a little stopwatch and starting it when the program begins and stopping it when the program ends. It's because we have a bunch of different processors. Like, I think you can imagine that the processor in this laptop that I'm using is a lot slower than these giant things that you have next to you, right? So if I have the same program running on my laptop, it's going to run slower than it will on those giant towers, right? And that has to do with processor speeds. Like, I have a 1.5 gigahertz processor, but maybe you have a 3 gigahertz processor, if we've heard those words before, or built our own PCs or something. That's just how many instructions that a CPU can do in a second. It can do 1.5 billion, it can do 3 billion operations per second. So we need a better way of timing a program, in a sense, okay, to see how complex it is. So there's a way to do that, and you go to the program itself. You look at the program itself, and you count some stuff, all right? So regardless of processor speeds, some programs are still faster than others. If you, like, take away this possibility, if you arrange for the idea that processors will have different speeds. I forget the technical term for doing that, but that is what we need to do. Regardless of processor speed, some programs are still faster than others. Here's how we can tell, all right? We're going to count the number of what I call basic operations in our program, all right? Basic operations, let's say that they take one step of execution. So they're something that a CPU can do in one clock cycle, if you know what that word means. It can do the CPU single operation. It can do 3 billion of them a second if you have a 3 gigahertz CPU. A basic operation is one of those operations, okay? They take one step of execution for whatever step means, and it's different for every processor. But they all do the same things in one step. So basic arithmetic, let's say that that takes one step of execution time. A plus, adding 2 things, subtracting 2 things, multiplying, dividing, getting the mod, comparing, takes one step of execution, let's say, all right? A simple assignment like make F22, put a value into a variable. That's a single step of execution. Printing to cout, let's say that that also takes a single step of execution time. These are kind of lies, but that's okay as long as we're within a constant factor of the truth. We'll find that out in CSCI 41. But let's count the basic operations in these 2 lines of code then. So int x equals y times z. Well, let's do like y times 2 plus z. Something like that. So that's one line, and then we can be like cout x. So those are my 2 lines. Let me like bring this over a little bit. Let's count the basic operations in those 2 lines. And these will be the same no matter which processor we run our program on. So all the math stuff takes one basic operation. So y times 2, that's one basic operation. Then we have this result. We need to add it to z. That addition will be another basic operation. And then we need to put the value into a variable with an assignment. That'll take a 3rd basic operation. Okay, see how I'm counting that? It's like 3 things are going on really on that one line. See how I'm breaking that down? Maybe we never thought of that before. And then printing to cout on the next line, that's just the one thing. Get the variable, put it into cout. That's one step of execution, let's say. That's 4 basic operations total in these 2 lines. Okay, so longer lines usually have more stuff going on. They take more steps, but it's still a constant number of steps. 4 basic operations in those 2 lines. Are there any questions about what I just did? I took these ideas, I looked for them in these lines, and I counted. because there are some other things that are definitely not basic operations, right? You can think of like summing a vector, summing all the values in a vector. That's not a single basic operation, right? It's made up of a bunch of tiny ones, maybe. But summing a vector is not a basic operation because there's a different amount of work you need to do for a differently sized vector. You need to do more pluses for a size 1 million vector than for a size 100 vector. Does that make sense? But you can count based on its size how many additions you're going to do. That is too high level. We need to go deeper. Count the basic operations only. So that's not a basic operation. Calling a function is not a basic operation because you're going to jump to the body of that function and start running that code. You better count those basic operations in the body of that function, right? So calling a function is also not a basic operation. Reading a bunch of ints until the user types -1, again, not a basic operation, but it's built using them, right? Because you're not sure how many ints you're going to read. It could be 1,000,000 before the user types -1. You're not sure, okay? So hopefully you see the difference. Things that take a single step of execution versus things that don't, that are built using those tinier things. And for most intents and purposes, you can think of all like little single line statements that don't do anything fancy like call a function. You can just consider those to be a basic operation or so. Like this is pretty much one basic operation. This is pretty much one basic operation. 4 though, really. Okay? Any questions about that idea? It's a bit vague, I know. Hopefully the example helped. Because now I have a question for you. Get together, see if you can come up with your ideas. Let's write it down this time. Let's see if we can get into groups and write down our best guess. So please go to the written ice page and I'll clear it out. Let's see what we're thinking. I'd like to know. Boop. So here's my question for you. How many basic operations is this loop? You remember what it means for a for loop to execute? It does this line once, it does this line a few times, this line a few times, this line a few times. See if you can express that mathematically. And here are what basic operations are. I'll put that here. So take a few minutes to count this and write your answer as a group into the Google Doc, please. Are there any questions about the question, by the way? Are you good with that? You understand the objective, even though it might be a hard question? All right. So take a few minutes to try that and see if you can write down an answer. Write down your best guess. I see some assignments, some comparisons. What is an increment but an assignment plus an addition? All of it executes and it finishes. Yeah. No. N could be anything. N is a variable. How many times is the loop going to execute? N times. So can you get a mathematical expression in terms of N? Take about 20 more seconds to get something in. Come back and discuss. All right, that's my timer. Get your best guess in there, please. If you didn't finish. But did we figure out anything? Very good. A lot of us noticed that n is something we have no control over, right? It's just a variable. The number of steps involves n, whatever n is, and so that better appear in your answer. Very, very good. Okay? We're unsure what the constant is out in front of n, and that's not really important anyway. But let me do this very slowly with you now. So, all right, this line runs once at the very beginning of the for loop, right? It's an assignment. So that's one basic operation. One basic operation. So it's 1 plus a bunch of other stuff, right? Then we have to worry about how many times is this comparison going to happen? How many times is I++ going to happen? How many times is the body going to do its thing? The body, by the way, has how many basic operations just to do this line? Yeah, I'd say it's printing out 2 things. And so it's 2 basic operations. 1, 2. Not a big deal, but if you want to get technical, I say it's 2 things. 2 basic operations for that. And then it's 1 basic operation for the comparison. I++, how many basic operations to do that? That's secretly I equals I plus 1, which is both an addition and an assignment. So 2. See that? Secret. So it's okay if you didn't get that, but this is kind of how you have to analyze stuff. This is what I'm going to teach you how to do in CSCI 41 when you take that. So with that in mind, we've got to figure out how many times all these things execute. Like this one's just once, but the rest of these are in a loop, right? So I is going to range between 1 and n. So we are going to run this line. Like the body is going to happen n times, right? N times do we hit that body. So n times we hit the body. And then also after the body's finished, we always do I++. So it's like connected to the body, right? So I would say that is... we always do the comparison, do the body, do the plus plus. So that's what? 1, 2, 3, 4, 5 basic operations done n times 5. But then I becomes n plus 1, right, at the very last iteration of the loop, and we're not sure if the loop is done yet. So this I less than or equal to n comparison happens 1 extra time to notice that we need to stop the loop. The rest doesn't continue, but we need to compare 1 last time and have it be false for the loop to stop. So there's actually 1 more comparison out here. That is the correct count given this idea. Okay, does that make sense? This is secretly 5n plus 2 basic operations, all right? And we'll learn in CSCI 41 that like this 2, like when n gets large, the 2, of course, becomes microscopic. We can just get rid of that, call this 5n. And we'll also learn like 5n is so much better than like n squared. So let's just drop the 5 too. It's equivalent to some constant times n, we say. And so no matter what n is, the amount of work that we're doing grows linearly as n increases. Okay? Does that make sense? So we call that a linear time algorithm. As n gets larger, the amount of work stays proportional to n, linearly. Okay? So the graph of how much work you do based on what n is just a line. All right? And I think you can imagine that's much better than this graph, right? Some work needs to, like some work increases as n gets larger, even worse than a line. Yeah? So that is this question. Definitely a hard question. I'm not going to test you on this in this class, but I want you to get a feel for this because now you'll understand why some algorithms are better than others, right? Try and analyze them. Any questions about this question? So yeah, when you're doing this analysis, the method is, well, you count all the basic operations that is in your code, and then you write a formula for how many basic operations the program uses, how many it takes, usually in terms of a variable that you don't have control over. Maybe it's the size of the input, how many things the user gives you, how big your array is, / vector, all that stuff. You usually call that capital N in the literature, but we'll get to that later. So this is, if we take this lowercase n to be a capital N, this is, we're doing work that is proportional to n, okay? And that's what we're doing. So yeah, let's talk about this. Number of basic operations to add two ints. That's just a single x plus y line. That's a single basic operation. We call that constant time, okay? How many basic operations to sum n numbers? Well, that's n minus 1 pluses, right? So that's some constant out in front of n time, right? We call that linear time. It grows proportionally, linearly, in proportion to the input size n, okay? Where n is the number of numbers that maybe the user gave you. How much work is it to draw a n by n box of stars? Well, you have to see out a single star n squared times, right? There's n squared stars that you're printing. So that becomes n squared with a constant out in front work. So that's harder, more work technically. And you can quantify that difference. This is called polynomial time. Okay? So I want you to be thinking about this, like this is so much faster than this, which is so much faster than this, especially as n gets large. So this will really help you as you get ready to take CSCI 41, if that is your next step from this class. This is exactly what that class is all about, this kind of analysis. We finally care about how fast our programs run, right? This was linear time, this was polynomial time, boop, something like that. Okay? Any questions about any of that? Does it make enough sense? Okay. For my last trick of the day, I think, all I want to do is just talk about a new way to formulate an algorithm to do something. So, we talked about this a little while back, right? I gave you an example of this big thing, sum the squares of the numbers from 1 to n. We had to come up with an algorithm to do that, and we tracked the data, figured out what we needed to do first, split it into functions. That's a very good generic way to solve a problem. But here's another way to think about a problem. This one might work better for others. So think about an algorithm as a bunch of state that you need to carry around and a bunch of commands that you respond to that change your state. So there's going to be a concept of where I'm at, where I'm going. So like, here's my current state. The user tells me to do this thing. I get this command. Now the state looks like this. Maybe it's got lines in it. I don't know. And then I'm here, and the user tells me to do something else. I get a new command, and now I have a different state. I need to change my state in a different way. Right? Now maybe I have a checkerboard state. Okay? And then maybe the user gives me another command, and I change my state back to this. Something like that. So that's another way to formulate a program. Okay? To break it down into, okay, what is the state of my program at any given time? And then how do I respond to user input, to like a command? Okay? So yeah, that is another way to think about and break down programs. And this leads into something called a state machine. Okay? There are a ton of different ways to write programs. I've told you a million times that there's a million ways to write the same program, right? There's a bunch of, the technical terms are like architectures, patterns, design patterns. There's a bunch of those that people disagree on which is the best. There's a bunch of different architectures for programming and a bunch of different patterns for designing programs. Everybody thinks that the way that they love is the best. I don't make any assumptions about which one is the best here. I'm just going to teach you a few in this class. So here's another simple one right here that really helps you make a correct program. If you can break down your program into the way that I'm about to show you, it is almost effortless to write it correctly. Okay? So there is an answer to this. Is there a cookie cutter method for building a good program, a program that is technically beautiful, at least in my opinion, and one that is probably very likely to be correct. Here's one way. It's called a state machine. Okay? A state machine is an abstraction over this idea. Like a algorithm that I'm trying to build takes some state and it manipulates it using some commands. I respond to commands that change my state, pretty much. The technical term for those commands are called transitions. And so here are a couple state machines. The little circles or the ovals, those are your states, and then you can move around in those states in different ways with the arrows, with the transitions. And what they do is, if you can draw a state diagram that represents your program, they tell you exactly the kinds of operations you need to support in each different state, and then also that dictates exactly how your program gets to be run. Like, you cannot go from one state to another that does not have an arrow, and you must follow one of them. Okay, so here's some silly examples of a state machine. Here's the first one. Let's say that it's a very boring person's state machine. This is describing some person, and let's say that they start their life at home. There's a concept of a start state, and so maybe they start their life at home, and they wake up as an adult one day, and they have a job. All right. So they need to go to work to make money because it's a Thursday. And so they need to get themselves to the work state. All right? That is another state in this program, in this model of a human. And the only way for them to get there is to follow this transition. That's the only one that's going to lead you there from the home state, right? You take the train, you go to work. Okay, so this person is forced to take the train if they want to go to the work state. And let's pretend that they do. So now they're sitting at work. They spend some time there, they do their job, and then it's time to go back home, right? Time to go to home. And so they are forced to take the train back. That's the only transition that's going to get them there. Okay, do you see how this spells out exactly how this thing can run if this were a program? You are forced, if you want to go somewhere else, you better use this transition. That's the only one you're getting right now. And then when you're home, now you have options. Maybe it's nighttime. It's time to sleep. So you take the sleep state you take the sleep transition that brings you into the bed state, and then you sleep for hopefully enough time, and then you wake up back in home outside of the bed state. Okay? Any questions about that? It's a very simple idea, right? You make a bunch of states that your program should be allowed to go to, and then you dictate or you spell out exactly how those states can change from one to another. Okay? And it's really nice because you also say implicitly what you cannot do in this program. There's not multiple ways to get home from work. You cannot fall asleep at work because there's no transition from the work state to the bed state. Do you see that? If it's not there, you can't do it. That's a very, very wonderful thing that helps you as a programmer to make sure your state machine is correct, your program is correct. So that's how you can move around. And then, of course, you can follow this a few times. Maybe it's the weekend. You can stay home for a little while and sleep there, right? Or maybe you can go back to work on the same day if you forgot something or if you go home to eat lunch. But you can follow this state machine in any order. You can take a little nap while you're home, go back to work after lunch. You can follow these in any order as long as you respect those transitions. You have to do this to get to work. You have to do this to get out of bed. Okay? Any questions about that? Just a simple little diagram, but it's very powerful if you go and implement it. I'll give you one example at the end of class. Here's another example that's a bit more thorough. This is like a model of one of those ride-sharing apps like Uber or something. So here's how maybe the Uber app is implemented. You're a user, you're like, I want to go somewhere, and you click on somebody to get you there, and they come to you, right? So you start out in your Uber app in the trip requested state, right? And then it's Uber's job to get you the driver and to get you to your destination, right? So you start out in the trip requested state, maybe that's your start state, and then Uber's not going to take you anywhere unless your money's good, so they're going to force you to get to the payment state, and that is the only way you can eventually end up in the driver assigned to you state. Does that make sense? It's very easy to see. It's very hard to mess up this program now. You cannot get a driver without paying. It's impossible to get there. See how that really helps with making your programs correct and proving that they're correct? So you start in the trip requested state. the only way you can get to a driver is to make a payment. And so it tries your credit card, and if it fails, maybe it asks you back to try a new credit card. And eventually, going around this a few times, trying your debit card too, you're eventually going to get to the payment state, right? The payment might succeed, hopefully, and that will take you to the driver assigned state, right? The driver is allowed to say, no, that's way too far, and so they cancel on you. You're allowed to go back to the start. Or if they're like, all right, I'll take this person there, then the driver comes to you. They take you in their car, and eventually your trip is complete, right? That's that transition. And then Uber needs to give the driver somebody else to drive, and so they put the program into the driver unassigned state, and that's pretty much it. Okay, trip end. But you can see that this gives you some very strong guarantees about your program if you can break it down like this. You are forced to pay before you can ride somewhere. That's really, really nice to have. Okay? If you can spell out exactly how your program can run in all these different states, it's pretty hard to mess up the program. Okay? I'll show you how to implement a state machine. Are there any questions about this one? All right, yeah, so the trick is, the idea is, let's zoom back out. If you want to do something this way, if you notice that your program has this kind of property, these ideas of a state and moving around between states, what you do is you group your program into those different states that you can be in and the actions that can take you away from that state or keep you in it to transition you. Okay? So here's a silly example. Let's pretend that you are a state machine, and as far as I'm concerned, you are a two-state machine. You have two states. You have a learn state and you have a practice state as a student. Okay? So maybe you start out, you come in the class, you have nothing to practice yet because I haven't given you any assignments. So that's your start state. Your start state is the learn state. All right? And then you alternate between those states as I post stuff, right? If I assign a lab, you go straight to the practice state. And then you stay there while you're working on the lab, right? Something like that. So you can transition and stay in the same state, not a problem. And then when I have to start lecture again, you come out of the practice state and you start listening, right? You go back to the learn state. And hopefully you keep doing that as long as the lecture is not over, okay? So that is a state machine that maybe describes you. So your initial state, your start state, was the learn state. And you can also specify that some states are good ending states. This should be a final state. You can put another line within the circle, and that marks it as a final state. Your final state in this class is going to be the practice state because you'll be taking the final exam and then there's nothing else to learn, right? That is the state you will end on in this class. Does that make sense? So you can model anything with a state machine, including programs and people. All right, does that make enough sense? All right, here's my question for you then. Please finish the following state machine. Let's pretend that this is a state machine for a traffic light. We want to make sure that people don't crash into each other, right? So how can you make a single traffic light do the right thing? There are plenty of correct answers, but tell me what should be the start state when you turn on the traffic light. What are the transitions that take you between these states? Maybe that you can go one way but not another, right? Can a light change from red to yellow in the US? Something like that. In some countries it can. It'd be nice if they did it here because it kind of warns you that the light's going to change. But that is besides the point. So try this. Try to fill in the states. Fill in the transitions. Here are all the states. Multiple correct answers. How should you build this traffic light? See if you can come to an agreement as a group. Oh, it's take about another minute to draw something cool. All right. There it is. All right, we'll be looking into that. Okay. So, yeah, let's see what we're thinking. Let me go back to my notes here. All right, which is the right state to start in? I don't know. You turn on the traffic light, you plug it in for the first time. What should the light be? I think it's very safe. Like, that's the best answer, right? That's the safest option. Don't just plug it in and have it be green, because maybe you plug them all in at the same time. That would be a problem. So I think that's a good start state, but like, how can you get out of the red state? What would take you? Where could you go, and what would take you there? Yeah, you go straight to green from the red state. There's no way to go anywhere else, right? And I don't know. What's the transition? I like that. Yeah, no other lights are green. Maybe also there's a car waiting to go in this way. So there's been a car waiting. I don't know, maybe like greater than or equal to 1 minute. You want to give some other people time to go to, right? So yeah, that's exactly what you do with a transition. I guess once you're in green, can you go straight to red? No. You got to go in between. You got to go to yellow. So maybe, I don't know, the light's been green for 30 seconds. Maybe then it goes to yellow. 30 seconds later. How long does a light stay yellow? It's like, oh, nice. So, yeah, it depends. So use some kind of fancy mathematical formula to get you to the red state. Like, let's just pretend it's 3 seconds later or something like that. But that's like a standard traffic light. Does that make sense? Is that kind of what we got? There are some ways to do weird things, right? They can flash a yellow light. I forget why, but you can totally flash a red light. You can stay in the red state if there's like a power outage, right? It goes straight to the backup battery and then it stays flashing red. So if there's like an electrical failure, you can stay here. And I think you can come up with others, but I think that's good enough. Are there any questions about this? Is that kind of what we got? Let me put this arrow over here just to specify that this is the name of the transition. This is the arrow that means we're starting here. That's the start state. Okay? We good with that? Fun little exercise. There's plenty of ways to implement this. And in some countries, you can go in this way from red to yellow. Like in the UK, the red and the yellow light up all at once before it turns green. All right. So if we're good with that, I want to show you a non-toy example of a state machine, and we'll program it, and it's going to be great to solve a non-trivial problem. So let's make a state machine to count all the words in a string. Okay? We're going to count every single word in a string that we're given from the user. So maybe we have the user type a whole long line. And notice right now this is a non-trivial problem, because you can't do something like, all right, I'll just count the number of spaces in this line and subtract 1, and that's the number of words. Because you can do something silly like this. The user could have typed hello, comma, space, world, exclamation point, and then they can type a bunch of spaces, 1, 2, 3, blah, space, 42, then we're done with the input. So the user can type a million spaces before the next word. So just counting spaces is not going to give you the answer, right? So this is a non-trivial problem, and it has a very beautiful solution with a state machine. This is actually an algorithm that I learned when I took CSCI 40. So I'm teaching it to you now, passing it along. So we are going to do the following. We are going to run our state machine on the characters of the string, on the characters of the line. So we're going to look at the H, look at the E next, look at the L, and we're going to use those characters to transition our state machine. So the transition is going to be what character we just saw. And we're going to keep track of whether or not we saw a white space character, so a character that is space returns true, right? Because it could have been a tab, could have been a new line, could have been a bunch of stuff other than just space characters. So we'll keep track of whether or not that character we saw was white space or not white space. And so the key idea, the way that this is going to work is we'll notice that white space separates words. No matter how much there is, like one or multiple pieces of white space, that separates the words, right? Every non-space character that we see, like we saw this is a space character, but we see this one, it's a non-space character. That means it's either part of a word, right? Part of a word we've already seen, or it's a brand new word. That W is special. The O is part of a word we've already seen. We need to differentiate between those two, right? The R, the L, the D, those don't count as a new word, but that W does. Okay? So here's the answer. We're going to make a two-state machine, two states. We're going to have an outside a word state. We're going to have an inside a word state. Let me draw that better. I sure hope that's enough space. I'll figure that out soon enough. So those are the two states, and we're going to run this state machine on each character of the string that we're trying to count the words in, one by one. And so at the very beginning, we haven't looked at anything. We are outside of a word, right? We have not seen any words yet. We haven't seen anything at all. So our start state is going to be the outside of word state. Okay? And then let's see how we transition. Just keep track of whether or not you're outside of a word or inside of a word, and this will actually give us the answer. All right? So the very first character I see is an H. I'm definitely inside of a word once I saw that H. So if I was outside and I saw a non-space character, I'm totally inside of a word now, right? So that transitions me here. Non-space. Okay? And then when I see the E, like I'm here now, I saw the H, I'm inside of a word. I see an E now. I'm still inside of that word, right? The L, the O, the comma, all of those, still inside of that word. Does that make sense? So as long as you keep seeing non-spaces, you're still in the inside of a word state, right? You're still inside of some word that you're currently reading. But then I get to this space, right? And I'm in the inside of a word state. I need to transition on that space, right? If I see a space character and I was inside of a word, I'm totally outside of one now. A space is not part of any word. So I'm going to transition this way. If I see a space character, okay? And then I just keep on going. Next I see a W. Or if I was here, like I saw a space character, I went to the outside of a word state. And then I see another space character, I'm still outside of any word, right? So if I continuously see a bunch of spaces while I'm outside of a word, I'm still outside of a word. Does that make sense? So this is the state machine that you run, and the only trick is to keep a count variable and start it at 0, of course. And then you feed every character one by one through the state machine, and you count when you see a new word. Which transition notices a new word? There's 4 here. This one, this one, this one, this one. Which transition notices a brand new word and we should count it? Which one? Yeah. The second I was outside of a word and now I'm inside of a word, that means I found a new word, right? This transition right here is the special one. So if you would just remember every time you follow this transition to additionally, of course change your state and everything, but additionally add 1 to count, that will correctly count all the words in your string. Let's watch it. So count starts at 0. I see the H. I was outside of a word because that's my start state. I just saw a non-space character. So now I'm inside of a word. Count as 1. So I'm supposed to add 1 in that transition only. And now I see the E. I'm still seeing a non-space character. I'm still inside of a word. I see the L, the O, the comma, still inside of a word. It's not a space. But now I see the space. And so I was inside of a word. Now I'm outside of a word. I'm ready to see a new one. Okay? And then I see the W. I was outside. Now I'm inside. I follow that transition. My count's 2. ORLD, exclamation point. I think you can imagine those keep me inside of a word. Oops. Give me an eraser, please. There we go. And then I see a space. I'm inside of a word. I see a space. So I transition to outside of a word. Ready to see, hopefully, a new word soon. But no, I stay outside of a word for a while because I keep seeing space characters, right? I see another space, stay outside of a word, see another space, stay outside of a word. But then I see the B for blah. I was outside, now I'm inside. I saw a brand new word, so counts 3. The L, the A, the H, they keep me inside because that's a bunch of non-space characters. I see a space outside of a word again. And I see the 4 on 42. That's a non-space character. I'm inside of a word again. So now the count's 4. And then I see 2. I'm still seeing a non-space character. I'm still inside of a word. And so that's the last state I ever see inside of a word. I'm done with the string now. My count has been set to the correct number of words in that string. Are there any questions about that? That state machine will correctly count the number of words in any string you give it. That's pretty nice. So, all we have to do now is implement this. So let's code this up. Let's make it a library, in fact. And so let's make a bunch of separate files, and maybe we'll make a test as well. Okay? So, let's make the main file first. That will help me, I think. Actually, let's make a new folder for all this. I'll call this count words, because the whole library is going to go in there, and the main file that runs the library. Oop. All right, so, I don't know. We need a bunch of files, including like a file that actually uses our library. So let's call that main.cpp as usual. And let's call our library, I don't know, include, how do I call it here? Count words.h. That'll be the header file that holds the count words functionality. And then I'll also need, can I steal it from lecture 11 somewhere? Oh, sorry, // lecture. Oh, I guess 12. And then I have counter that has a main.cpp. Let me steal the assert true from that one, so we can eventually have a test. But before we get there, let's pretend that we have our library. Let's use it. So let's make string line. I guess I need strings. Let's see, what do we need next? We like cout, enter a line of text. And then I'll get it. Get the whole thing. Get line, cn, line. And then I'll call count words on it. Count words on my line, new line. So my library, my count words library, is just going to implement this one function. called count words. Okay? So let's get that working. So the header file, countwords.h, is going to declare what is in my library. All right? Also remember your header file guards. But the one thing that's going to be in this library is going to be our count words function. So it's count words, it takes a word. Let's take it by reference, string s. So I need string s, returns an int. One thing you cannot do and should not do in a header file is use namespace standard. Because somebody who uses your library might not want to use namespace standard. And remember what happens when you include a library, include a header file? It copies and pastes everything there. So if I wasn't trying to use namespace standard here, and I was using it in the header file, I would suddenly be using it in this file too, right? It's getting copied and pasted. We don't want that. We want to give the user the option to use it or not. So we are forced to say standard : string, like we did on the very first day of class, right? And let's make it a constant reference, because why not? We don't have to change the string. We just got to count the words in it. So that'll be my declaration of the program. And actually, because this is including string for me, I'm forced to put it here so I can include the string class. It's getting copied and pasted when I include it. I don't actually have to do this one. It's already there. That's kind of cool. And then in the CPP file, I'll go and implement this function, right? So, count words.cpp. I'm going to implement this function. Customary to include your header file .h, because that'll give me the string type. See how that error goes away now? And in the implementation file, you're totally allowed to use namespace standard. That's just for you. Nobody else is going to copy and paste this file. So I can say string here if I want to. Okay? So that's the idea. Yeah. Let me implement the state machine for you now. So here's what you do. You keep track of which state you're in. You're either outside of a word or inside of a word. Let's just store which state we're in as a string, right? We just need a state variable. Let's just make a variable called state, string state, and let's start it outside. Just be like all caps outside string. This means that we are currently in the outside of word state. We'll just keep track of our current state in this variable called state. Why not? Does that make sense? So this is how we program a state machine. Either outside or inside, we gotta remember which one we're in and then transition appropriately. Okay? So that's that. Yeah, and then we're gonna run the state machine. Our count's 0, right? We want to run the state machine on every character in S. Okay, so I don't know. Let's do it the old way. For int I equals 0, I is less than s dot size I plus plus, and then we can get the current character current char at this index equals s at I, and so just run this character through the state machine now. All right. So how do we run it through the state machine? Well, it depends. What we do depends on whether or not we're inside of a word or outside of a word, so usually it does. In this case, it actually doesn't, so you could simplify what I'm about to write. I encourage you to try that. But you just have two options, like, all right, am I trying to transition out of this state? Am I currently in this state or this state? If state is outside, I got to transition based on what I just saw with that knowledge. Else, the only other option is the state was inside, right? So let's transition with that in mind, right? So then, if the state was outside, we need to transition if we saw a space character or a non-space character, all right? We need CC type for that. That'll tell us which kind of character we saw because that has the isSpace function. So if isSpace current char, if that current character is a space character, how does that change our state? Well, we were outside, we actually stay outside. So we technically don't have to do anything at all. But let's just for fun spell it out. State is outside, even though it already is. So that's how I transition if I see a space character. Otherwise, then I must have seen a non-space character. If that happens, I need to make this transition, right? I was outside, I need to become, my state becomes inside, and then I also add 1 to count. All right? That's what we got to do. So otherwise, we saw a non-space character from the outside of word state. So the state becomes inside a word. Let's call it all caps inside, and then count plus plus. We just saw a brand new word. Does that make sense? The same thing is mostly true for inside of a word. If you see a space character, you go to outside of a word. If you see a non-space, you stay inside of a word. So you can pretty much copy and paste this. So it transitions properly. The one thing you can't do is keep counting, right? If you're inside of a word and you still see a non-space character, you're inside of the same word, not a new one, okay? So you can't add to your count there. But this is going to implement the state machine. Not if else, with an if else inside of it. Are there any questions about that? That's me implementing the state machine. Every transition from every state. That's all you got to do. Okay, where's the end of this? That's the else. Is that the function? No, that's the for loop. All right, so the function needs to return the count. Because we were supposed to return an int, right? Int count words. So return that count, and I believe it should be happy now. So I have my implementation, my header file, my main file that actually uses it. And so when I compile, I got to give both implementation files, main.cpp and countwords.cpp. And I will call that, I don't know, let's call it countwords this time instead of main. Call it whatever you want. So enter line of text. What was it? Hello, comma, space, world, exclamation point, 3 spaces, blah, space 42. Those are 4 words in that line. Okay? If you try this enough times, like hi, space, 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 mom, space, 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 still gets it right. That is a correct implementation of the state machine. Are there any questions about that, what I just did? Definitely study this code. There's a lot going on. But hopefully it made enough sense as I was implementing it. All right, so let's make a test. Instead of running this on user input, let's make a test instead. So let's comment all this out. And instead of that, let me make a test using our assert true function. So instead of all this, let's make one test. And the test can live in its own little function. And we'll call it test count words. I'm going to run a single test, single unit test. And we'll use the assert true function. So I don't know. We have to make a string, right? We need to call our function and test it. So we better make a string that has a certain number of words in it, right? String s equals, I don't know, hello, comma, space, world, exclamation point, space, 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 blah. You can have more than just space characters, like a new line is a space, a tab is a space, a bunch more spaces, and then 42. Okay? So there are 1, 2, 3, 4 words in this string. Our count words function better give back 4 then. So assert true that count words of s, whatever that gives back, is supposed to be what I expect to see. Should have been 4, right? So count words in a 4-word sentence. That is a test. Calling assert true. So I have what I'm getting back is going to get replaced by this, right? Hopefully it's right. And then what it should have been was 4, because there are 4 words in this string. Okay, and here I am calling that test function, which calls assert true. Recompile, rerun, and yay, it passed. And so you want to make as many tests as you can to try different things. Like one edge case is just there's a bunch of spaces in the string. There should be 0 words in that string, right? Count words in a 0-word sentence. Is that better? Count words on a string that's empty or a string with just spaces inside of it. Better not ever increment that count. And because we made our state machine the way we did, it's pretty hard to get it wrong, right? It's only ever going to go to that other state if we transition from outside to inside of a word. We only ever transition to inside of a word if we see a non-space character. pretty hard to get it wrong. And so that one also passes. Okay? Any questions about that? We're still good? All right. So I think that's everything. Let's see here. So this was if I were to have released a lab today. Some semesters there's a holiday involved and I do that, but not this time. So I have a feeling that is all. Yeah, so no new lab today because you got one due week 8. So next week, which is week 8, I will assign the next one. Okay, so just work on what you got, what is out at the moment.